So this is, we're going to make a little tank game. First of all, we're going to make a little tank class. So it has position and a direction, and also we have this second order, the next order rather, speed, angular velocity, and also this is just the player's control. So this is, we're defining this, we don't use health and kills, we're defining this as a defined packable class, basically a wraparound def class. And it's inheriting, this one's inherited from Zoetrope game state, and we have this pack slot thing, so pack slot is used by defined packable class, so we want this saved. Okay, these are the moves, so there's three parts to it. There's the state, there's the moves, and then there's our logic, which is what we have to define. So the same kind of thing, they basically just have how much you're moving by. This is our actual interesting game logic, so this is where what actually happens to the tank every tick. So it's a tick-based game. We're using fixed point arithmetic, so we use special cost 16. I'm not using the floats because they tend to be a bit sketchy on different machines. Yeah, so now this is a specialization of applying a move, which is a player join move, which is a Zoetrope move. So we're specializing it just on our own tank game, so we call the original method, and then we add the tank into where we need to do this, so this bit of code does. Looks a bit longer than it probably needs to be. So that's this one your player joins, this one's when a player leaves, so we're just setting it back to null again, wherever it was, and call through again to remove the player because it's another override. These are the steering moves, so all you're doing basically is whatever move comes in, we just set the tank value the same. Dead simple. This is the update logic. What we're doing is updating all the tanks with the logic we said there. So that's specialising on Zoetrope. Okay, this is just drawing the average round trip time. So you'll see this when we go up, but that comes out of Zoetrope. It'll calculate the average round trip time for you. Yeah, there you go. Then this is the main method. So we set up some simulation delay here. And this is just setting up the screen we're doing. You know, this is a basic window, high-level macro to do that. All this basically, this little block here is doing is checking to see when a state changes or when a game changes, and we change the screen. Yep. So go between the login screen and the game screen itself. And this is where this is the rendering of the game. But here is the where the actual stuff is, all the business happens. The packets get sent, they get received, game states get replayed, all that stuff. We don't have to write that. Inside game render, it's just a regular kind of OpenGL, dead simple thing. We're just rendering the states of the game. I'm actually rendering all the states and then clearing with half transparency every frame. So this is just going in tank render. All it is drawing a little square for each tank, just rotating them using the values actually out of them. So yeah, we're drawing all the states from the Zoetrope, which is, there's loads of states in memory, so we can rewind to any previous state, and we put a 50% transparency over each one, so you can see going back in time what they look like. That's about it for the render, I think, really. And then the stuff below is just drawing the on-screen display. Okay, so let's run it. This is all pre-compiled, it's all loaded in the image. This is the actual, what the login screen looks like. I didn't show you this, but it doesn't matter. Just starting the server, we're going to start another one in a window I prepared earlier. So there you go, start. Now we've got two of them. Well, so I haven't actually started these, we started that server, and we haven't connected any clients yet, so enter the secret password, and we'll connect to the server. Yep, so that's running the same process, but we still have this lag simulation, so there is a, you know, so we've got a measured round trip time, and you can see the states in the past now. So let's actually prove that this works across, well, this isn't actually across the network, but they're separate processes. So we'll connect another one. And here he goes. Okay, mega lag, but we can see now if I can control one of them, and it appears on the other screen. This is with extreme lag, so I mean, this would cope with, the game would still run under heavy lag conditions on the internet. Obviously, you wouldn't want to be running like this. You'd probably disconnect and reconnect to one with a lower lag. But anyway, this is emulating high round trip just to prove the system works. So you can see with the trails that are left behind, where we change our mind on one of the games, you can see the correction that happens on the other. You wouldn't want to display this game information directly. Oh, here we go. I'm just proving that a reconnect works. You wouldn't want to display this game information directly. You'd probably want to put a separate graphics layer on top, and rubber band them towards these positions. This is actually printing out the raw data. But yeah, that's about it for now.